Hello everyone, welcome to my group theory lecture. In this lecture, we study Lagrange's theorem. Okay, first we discuss equivalence relations. So here's the definition. A binary relation R on a non-empty set S is a subset. Okay, so it's simply a subset R uh, of S Cartesian product S. If so, since it is a subset of the S Cartesian product S, the elements of R would be the ordered pairs, right? So if an ordered pair AB is in R, we say A is R related to B, and write uh, the following notation: A, R, B. A binary relation R on a set S is called an equivalence relation on S if it satisfies the following three axioms. So first one, for any A in S, A are A, which means that A is related to A itself. Okay, so this property is called R is is set. We say in this case R is reflexive. Okay, R is reflexive. And next axiom is for any two elements A, B in S, if A is related to B. If A is related to B, B is also related to A. So this property, we say R is a symmetry. Okay, R is symmetry. And last axiom is for any A, B, and C, three elements in S, if R is related to B and B is related to C, then A is also related to C. So this property is called transitivity. In other words, we say R is transitive. Okay, so the a binary relation with three properties: reflexivity, symmetry, and transitivity is called an equivalence relation on S. Let us take a look at a couple of examples of equivalence relations. Actually, these both are more than just examples, very important examples. Okay, so we are going to see them a lot more often later on. Okay, so first example, we are going to define this binary relation here. It's a little complicated looking. Okay, uh, we are going to call this congruent modulo n, congruent mod n in short, on Z. So we define this binary relation by the following: for any AB in Z, two integers AB, A is congruent to B modulo or simply mod n if n divides A minus B. In this case, this relation is an equivalence relation on the set of all integers. And this relation is called the congruence relation. Congruence relation modulo n. Uh, well, to give you a heads up, this is particularly very important, actually this is a very important example of a class of equivalence relation. Okay, so in more abstract algebra, well, what we are learning is actually, called the abstract algebra, but in modern perspective. The name abstract algebra actually came from, you know, the comparison with the, like even older like algebra, which is mostly concentrated on like solving, equations and so on and so forth. Okay, so from that perspective, what we are learning now is called the abstract algebra, but the truth is, it is no longer that much abstract. Okay, so we have more actually abstract algebra, more general. So the such algebra is called the universal algebra. So from the perspective of universal algebra, right? There's a class of equivalence relations that preserve operations as well, and so those equivalence relations are called congruence relations. The name congruence relation actually there came from this particular example because this example does the same thing. It is not just an equivalence relation, but it also preserves operations. Okay, so anyway, I'm going to stop here. I'm not going to delve more into that. And so let's prove this. Okay, to do that, let's go to my notepad. Example. Uh, okay. This congruent modulo n is an equivalence relation on Z. So that's what we want to check, right? So here's a proof. I'm going to use a different color. So here's proof. Okay, so we want to show reflexivity, symmetry, and transitivity, right? So we want to show that this relation satisfies those three axioms. So first one is reflexivity. Okay, so for any, so in this case for any a and z, right? For any a and z, for any integer n divides a minus a, which is equal to 0. Well, you know that, any non-zero integer or any non-zero number in general, right, divides 0, okay? So this implies that a is congruent to a modulo n. Oh, by the way, I forgot to mention one thing. Okay, so before I go further, forget, before I forget, I would like to mention this. Earlier I mentioned that this relation, equivalence relation, also preserves operations. Okay, that's actually very important for us, and we're gonna come back to that later on, and we will study more about that. Okay, I said earlier, like, I don't want to delve into that, but just for now. Okay, but we are gonna come back to that point. It's very important because that allows us to to come up with a new group structure. Okay, so that's very important thing, and this equivalence relation plays a very important roles, not only in algebra but also like a number theory, even cryptography. Okay, so right, so we are coming back. Okay, so next property is symmetry. Next axiom we want to check. Symmetry. So here for any two integers a, b, and z, okay, if a is congruent to b modulo n, and b is congruent to c modulo n, now that implies, by definition, what this means is n divides b minus a, and I better use parentheses. Next one, n divides c minus b, right? I'm just following the definition. So n divides b minus a and n divides c minus b. So n divides b minus a plus c minus b. Which equals, so here, b cancels out, right? B cancels out. And this equals c minus a, right? C minus a. So what do we have? N divides c minus a, which means a following the definition, A is congruent to C modulo modulo, and I got carried out a little bit. Okay, sorry. I meant to talk about symmetry, but actually I ended up doing transitivity. Sorry about that. So I'd like to do things in order, but that's okay. So this is transitivity. Transitivity. Okay. Okay, so now back to symmetry that I initially intended to prove. Okay, symmetry. So here, right, also there's something else I need to fix, right? I needed 3 of them. I don't know what I was thinking. Okay, so for any A, B, C in Z, right? Okay, everything else is okay. Right, so for any A, B, two integers A, B, if A is congruent to B modulo N, by definition, N divides B minus A, all right? N divides B minus A. So what does that mean? That means B minus A B minus A equals N times K, right? For some integer K. So A minus B, in this case, right, can be written as N times negative K, right? And negative K is also an integer, which implies, by definition, B is congruent to A modulo N. So we have shown that this congruent modulo N is an equivalence relation on Z, because it satisfies three axioms: reflexivity, symmetry, and transitivity. Okay, let's move to the next example. So here we have a group and a subgroup H of G. We have a group G and a subgroup H of G. We define a binary relation R on G by the following definition. Okay, so right, so by the following. For any two elements A, B, and G, A is related to B if A, B inverse belongs to H. Then R is an equivalence relation on G. So, we are going to see this relation, equivalence relation, a lot later on. This is also very important for us. Okay, so let me get to my notepad again. So next example, so G is a group and H is a subgroup, right? So we have here, we define the a relation. Of course, here what I mean by relation is binary relation. We are considering only binary relation, but in general there are like a ternary relation, and so on and so forth. Okay, more general relations. R on G by the following. So for any A, B in G, A is related to B if A, B inverse is in H. So we want to show that, right? So then R is an equivalence relation on G. Okay, so we prove this. Okay, so first the reflexivity. For any A in G, A times A inverse is identity. and identity belongs to H, sorry. Identity belongs to H because H is a subgroup, right? And this means, by definition, A is related to A. That's easy, right? Symmetry. So this time I'm going to pay attention, okay? So I don't end up, doing transitivity like before. So for any A, B in G, right? If A is related to B, we want to show that B is also related to A, okay? So that implies, by definition, A, B inverse belongs to H. Since H is a subgroup, okay, and A times B inverse is in H, its inverse is going to be also in H as well, right? So, here, A, B inverse, inverse, okay? So what is this? This is actually B inverse, inverse, A inverse. Okay, so this is one of the group properties. I think that this is also one of yes, actually not what I'm thinking. I know that this is one of the exercise problems. Okay, so one of the you will find it in one of those problem sets. Very important, okay, property. Very basic and important property of the one of the basic and important properties of groups. So anyway, this equals B A inverse. So this has to be in H as well. And this means by definition B is related to A. Last one, we want to show transitivity. Okay, so for any, we need the three elements, right? For any A, B, and C in G, right? In the group G, if A is related to B and B is related to C, then what this means is A, B inverse belongs to H and B, C inverse belongs to H, right? Now, H is a subgroup. It is closed under the group of operation. So, and also we have these two belong to H. So their product has to belong to H also. So A, B inverse times B, C inverse equals, by associative law, okay? uh, this can be written as where the group operation is associative law, as you know, right? So that's A. This equals A, B inverse B, C inverse, and that equals A, E, C inverse, which equals A, C inverse, and that has to belong to H. Okay, so this implies what this means is by definition, A is related to C. So that completes the proof. Okay. I think this is a good point to stop, and because my intention is always not to make my lecture video no more than 30 minutes. But then that is just an intention. I always tend to break it because sometimes I got carried away. I get excited every time I talk about math. I get excited, so I just don't watch my clock. But this time I was watching, so I'm gonna stop here, take a break, and we'll continue in my next lecture. Okay, so thank you.